This recap is the second of two that helps you review for your first summative problem set or SPS1. We tackle lectures 23 to 26. So you may pause the video or you may take time checking the contents of this recap. We start with lecture 23 or Biot law. We glance through the position unit vector before solving a simple problem just for warm-up. It's good to review what the r-hat vector is since its presence is ubiquitous in magnetic field calculations. In a nutshell, r-hat is the unit vector of the position vector. It must be clear that it starts from the source and points toward the field point. You can see the r vector as the thinner and longer vector on the right, color black, and r-hat as the shorter but thicker blue vector. It is explicitly calculated as the position vector r divided by its magnitude. Again, very important, it goes from the source towards the field point. It's a very common mistake. Here we see the Biot law used to calculate the magnetic field at a point due to a single point charge. You can immediately see that the velocity v is cross to r hat. The distance between the charge and the field point appears squared in the denominator. A new constant appears. While it may seem confusing at first, especially we just discussed a quantity with mu sub naught is not the magnetic moment but rather the permeability of free space. Its usefulness appears in future subjects such as magnetic materials and inductance, but for now, its value is what is most important to us. It's rather easy to remember. It's 4 pi times 10 raised to the negative 7 henries per meter. Now, as Biot law is a cross product, its magnitude may be expressed in terms of the angle between the velocity and position vectors, or phi, via the sine function. We use this formula for a bunch of problems for single or multiple charges via the superposition principle. Let's go over an example dealing with two charges. So on the left, we see a charge plus q situated on the positive y-axis and a charge plus q prime on the negative y-axis. Both charges are at a distance d away from the origin, which is our field point. Charge plus q is moving towards the right with the speed v, and charge plus q prime is moving to the left at speed v prime. We want to find the total magnetic field at the origin due to these two charges. Now, from the principle of superposition, the total magnetic field is just the sum of the magnetic field contributions of each of the moving charges. Let's solve for the contribution of the top charge first. We note that its velocity is v I hat, and its corresponding r hat vector, as you can check in the orange arrow, points at negative j hat. Plugging in values to the Biot law, we have b sub q is equal to mu naught over 4 pi times qv I hat cross negative j hat over d squared, which then results to negative mu naught over 4 pi times qv k hat over d squared. Solving for the magnetic field contribution of the bottom charge q prime, we first recognize that v prime points in the negative I hat direction and r prime hat, or the unit position vector for q prime, or the blue vector, points at the positive j hat. Okay, then we plug it in the Biot equation, and solving the cross product gives us the following. bq prime is equal to negative mu naught over 4 pi times q prime v prime k hat over d squared. What you notice here is that similar to bq prime also points in the page. Now we go back to the total magnetic field. We substitute the values of bq and bq prime, and then we try to clean up the expression. And after doing so, it gives us b is equal to negative mu naught over 4 pi times qv plus q prime v prime over d squared times k hat. Now, you have to be careful in dealing with the cross products because this can spell the difference between getting the correct answer and being left with an algebraic mess. You should also note that the total magnetic field is pointing inside the page. If you make a mistake with the sign, sometimes it cancels out to 0, so you really have to be careful with that. Lecture 23 ended with calculating B of point charges using Biot law. As with previous lectures, we can transition from discrete points, or discrete charges, towards a continuous stream of charges, or currents. So for lecture 24, we focus on the magnetic fields due to current carrying segments. Let's change the pace by beginning with the general case immediately. For an arbitrary segment, we can't just apply a band-aid formula to solve for the magnetic field due to moving charges. Since we want to transition from discrete to continuous distributions of charges, we transform the QV term to an IDL. Each element segment DL contributes a field dB. And adding all of these contributions, so okay, let's go back. These segments, these green segments DL, all contribute some sort of dB at this field point here. So I'm not sure where the dB is supposed to point at that. And adding all of these contributions via integration gives us a general expression for a magnetic field due to any wire segment, given by the following. B is equal to mu naught over 4 pi and the integral of IDL cross r hat over r squared. The shape of the wire is specified, depends on the problems. It usually is specified by the contour set up by DL and the bounds of integration depending on how specific your problem has to be. I've omitted some details in the calculations for some of the problems considering that this is just a recap. So you can always go back to the actual lecture slides or the book if you find yourself wanting for clarification or just hungry for physics. Our system for this problem, on the right, consists of finding the magnetic field produced by a very long wire segment, emphasis on very long, with a constant current I passing through it. So focusing on the figure on the right, the segment isn't as obvious, but then the current is being delivered inside the page. And as you can see, the light blue lines there are actually the magnetic field lines. Now, our field point is at a distance r from the wire itself. So let's say it's here. There you go. You may review the integration process for yourself, but trust me for now that the answer is B equals mu naught I divided by 2 pi r. Fight me later should the need arise. Its direction can be easily determined using the right-hand rule. If you point your thumb to the direction of the current, your fingers should curl along the direction of B. Now I invite you to verify this with the graphic on the right. The current points in the page, and the right-hand rule agrees with the clockwise movement of the magnetic field. If you want to be really specific, IDL points in the page, and then your r hat vector should be like so. Now, if this is your field point, and I use the right-hand rule, IDL cross r will give me the magnetic field at this point to be here. And if I complete the picture, I'll eventually get the circle. A lengthy but robust discussion on the attraction and repulsion of current-carrying wires, or parallel current-carrying wires, may be found in the lecture slides, lecture 24, or the book. But a quick run at the results may be worth going over. We know that the magnetic force experienced by a straight current-carrying wire is given by I prime L cross B, or I L prime cross B, where I and B are the current and magnetic field produced by one wire, and I prime B prime the current and field produced by a parallel wire. Newton's third law dictates that these two forces are equal in magnitude but opposite in direction, and with the knowledge of fields produced by the long wire segments, we arrive at an expression for the force per unit length given by F over L is equal to mu naught I prime times I divided by 2 pi r. The nice thing about this expression is that it's independent of the length and is just reliant, well, on the distance from the wires themselves. Moving on to lecture 25, we explore magnetic fields due to current carrying loops. As seen in the figure on the right, the configuration for this problem involves a circular loop placed on the xy plane that carries a counterclockwise current if you view it from the positive z-axis. Our field point is along the z-axis, a distance p from the origin. To be specific, this is our field point. We start with the expression for the magnetic field generated by an element current segment IDL. For brevity, we skip the integration and go straight to the result. B is equal to mu naught I over 2 times r divided by r squared plus z squared raised to the 3/2 power. It's rather a complicated expression. So let's explore trying to simplify it. At a special case where we determine b at the origin itself, so we set z equals to 0, this quantity simplifies greatly to, well, b is equal to mu naught I divided by 2r. Thankfully, its direction, as with previous examples, is determined by the right-hand rule. Point your thumb to B, and the other fingers should curl along I. Now, a few comments that may be lost in speed running this recap. Spotting the direction of B becomes complicated the moment our loop is not complete. So if it has an interruption, so let's say we interrupt it at this point. Now, what's the issue with that? This happens because we lose our symmetry the moment we don't complete the loop. So that becomes a big issue there. Now, we can also lose symmetry if we choose a field point that isn't situated at the positive z-axis. So let's have an example there. Let's say we choose our field point to be somewhere here. The moment that you place your field point here and you try to do the integration, you won't cancel out components, and instead of having only one component of the magnetic field, you'll end up with two or possibly even more. So the idea is, for simple cases, we want to make sure that our answers are as, well, nice and simple as possible. So if you feel like you need a refresher in re-deriving these examples, you can always go back to the lecture notes or lecture slides given to you from previous weeks, or you can ask your instructor. Now we're hitting the mother lode. Ampere's law is the last topic for this recap, but it is a crucial tool coming into the next few lessons after this. If you recall, Ampere's law is the magnetism counterpart of Gauss' law, where we solve for the magnetic fields by current counting. For Gauss' law, it was charge counting, if you remember Q enclosed. And here we abuse symmetry, similar to Gauss' law. This section starts with the formula for Ampere's law and a refresher on contour integrals as well as enclosed currents. We move on to solving B of a long wire and compare this result with the one obtained from Biot Savart. Part C involves a detailed discussion of the magnetic field produced by a current running through a cylinder, a solid cylinder, at field points inside and outside the actual conductor. Finally, we lightly touch on the magnetic field produced by a solenoid. So this slide is juicy, so let's start right off the bat by throwing in the equation for Ampere's law, which is given by the integral of B dot dl is equal to mu naught times enclosed current I inc. You may notice some familiar symbols, but let's reacquaint ourselves with each one. The fancy looking integral has two features. The C at the bottom indicates that it is a contour integral. This integration is performed along elements dl of the Amperian loop. You've seen this in the Biot-Savart law calculations already. The contour integrals aren't new to you. The circle in the middle of the integral indicates that your contour should be a closed loop. You've also seen the circle already, but in closed surface integrals such as in Gauss' law. This is crucial to Ampere's law because the right-hand side of the formula accounts for currents enclosed by the contour, or the Amperian loop. You cannot have enclosed currents with an open contour. So let's check the integrand. Note that in the contour integral in the left-hand side of the equation, or this part, the left-hand side of the equation, that the quantity of interest is not just dl, but rather b dotted to dl. The bits we add together are the components of the magnetic field that are parallel to the contour. So you can check the lower right figure. This example highlights, okay, this is B and dl. But then the only component of B that we want to get really is this, shall we say, B parallel, because that's the one that's relevant to the contour. The other component, or sorry for the bad drawing, B perpendicular, will not really contribute to the actual contour integral, being the owing to the fact that B perpendicular dotted to DL is just equal to 0. Now, because of this, we get the meaty or the relevant parts of B and add them together. So good, the left-hand side is done. Now we move on to the right-hand side, and we do that by digging deeper on I enclosed. Now, this graphic shows an example of an Amperian loop traced counterclockwise if you view it from the top, and it encloses three currents. I1 and I3 are pointing up, and I2 is pointing down. So an important question would be, how do we know which of those currents is positive or negative? You have to recall that when we determine the direction of the magnetic field by a Biot-Savart law, we use the right-hand rule. Point your thumb to I, and B flows in the direction your fingers curl. In the same vein, using the right-hand rule dictates the current signs for Ampere's law, especially the enclosed currents. Given that DL flows counterclockwise, we see that the right-hand rule, or from the right-hand rule, that I1 and I3 are positive currents, while I2 is the negative current. So how do we go about that? Remember that this contour, basically the result of that contour, is the component of B that is parallel to DL. Now, you curl along the direction of B as it flows counterclockwise, your thumb will point up. And that should tell you that all of the currents pointing up, or pointing the same direction as your thumb, are positive currents, and the ones that are opposing it are negative currents. So to be specific, I enclosed for this instance should be equal to, so I enclosed is equal to I1 plus I3 minus I2, at least for this example, and for the fact that you are following a counterclockwise contour. Something should nag you from the previous slides and the previous examples, so let's tie that loose end. Notice that from the previous slide, you just assumed that we should traverse the contour counterclockwise. Because if you notice, this will dictate whether it's I1 and I3 that are positive or I2. So must the rule of the counterclockwise path reign eternal? Well, the answer is not really. Turns out, you could choose either path, and the sign of I enclosed should follow suit. So, while at first glance it may seem like the answer will actually change, it doesn't. So let's consider two cases. In the first case, let's enclose a straight current carrying wire pointing out of the page with an Amperian circle centered by it. Now, I dictate how I want to travel the loop, so I say let DL run counterclockwise as usual. The outward going current imposes that B should flow counterclockwise. You may want to do this via right-hand rule again. So this means that throughout the integration path, all B and DLs are actually parallel. So let's try it again. Our DL is arbitrarily set to be counterclockwise. I is pointing out of the page. So I point my thumb towards the direction of I, and my B should curl in the direction of, or sorry, my fingers should point in the direction as B flows. So notice that at every point of the contour, for example here, or here, DL and B are parallel. So what does that mean? The dot product B dot DL will always be positive. So after you perform the integration on the left-hand side, what you end up with is a positive valued left-hand side. So what's the nice thing about this? As checking the right-hand side, the counterclockwise flow of DL indicates that the currents pointing out of the page are positive. And that's us using the convention from the previous slide. This means that I, and eventually the whole right-hand side, is positive. So we have a positive left-hand side, and we have a positive right-hand side. Now let's work with the other case. Now for the other case, we have the same current pointing out. So it's the same physical system. And we practically have the same Amperian loop, but then there's a slight change. This time, I want to run DL clockwise. So you notice that compared to the first example, DL is actually pointing in the opposite direction as B. So what are the consequences for choosing that? B still flows counterclockwise since we didn't really change the current from the previous case. But since our DL flow is reversed, notice that in this case, all of the B's are anti-parallel to the DLs. And all of the B's dot DLs then become negative because the angle between B and DL is 180 degrees, or pi. The resulting integral then on the left-hand side of Ampere's law, or this part, should be negative, right? Because all of the integrands, when you add them all together, they're all negative, so you're going to end up with a negative left-hand side. Checking the right-hand side then, the clockwise flow of DL indicates that the currents pointing out of the page are negative if you follow the convention from the previous slide. This means that I, and consequently the right-hand side, should be negative too. And this is indicated by the negative sign here. The negatives of both sides of the equation cancel out, and all is well. So whatever convention or whatever choice of the flow of DL you choose for solving the problem, it should cancel out and should give you the same answer regardless of the convention. The most important part is for you to be consistent with your conventions. With all that dizziness out of the way, let's revisit solving the magnetic field due to a long straight wire at a distance r from the wire. But this time, let's change our attack from Biot-Savart law to Ampere's law. The current runs to the right, and the right-hand rule indicates that B flows out of the page above the wire and into the page below it. So if you want to be specific, you want to make it clearer, above the wire, B is going out of the page, and below the wire, B is going in the page, like so. Now, even if we're free to choose the flow of DL, as explained in the previous slides, we're not exactly given the same flexibility in choosing the shape of our Amperian loop and where it's located. So I have a short segue. Recall that in electric field calculations using Gauss' law, we chose Gaussian surfaces such that the electric field is constant throughout the surface. We choose the Gaussian surface that exploits the symmetry of the configurations. Now, for Ampere's law to work, we must choose an Amperian loop that takes advantage of the symmetry of the system. Because without symmetry, it's back to hacking the problem with Biot-Savart law and nauseating integrals. We choose the Amperian loop to be a circle of radius r centered at the wire. Now, for ease of solution, we also choose DL to run along the same direction as B. So B dot DL becomes BDL for all DL. With this, we can pull B out of the integral because B along all points of the Amperian loop is already constant, which is nice. The integral is then easily evaluated to be just the circumference of the loop. So notice here, once we're done isolating B out of the integral, this integral of DL just becomes the circumference of your Amperian loop. Now, the left-hand side of Ampere's law will then just be equal to B times 2 pi r, something very simple, unlike Biot-Savart. Dealing with the right-hand side of Ampere's law, we easily recognize that I enclosed is just plus I, remembering that our choice of DL flow aligns the positive current with the current that we have. Combining the left-hand side and the right-hand side, we get the following equation. B times 2 pi r is equal to mu naught times I. From there, we can isolate B to give us the final answer. B being equal to mu naught times I divided by 2 pi r. Noting that this is the exact result we got from Biot-Savart law without having to employ lengthy integral calculations. Now, I reiterate that while Biot-Savart law can solve a larger class of problems, Ampere's law can fast-track solutions as long as the system of interest is highly symmetrical. So that means, well, it's actually parallel to the relationship of Coulomb's law with Gauss' law in electrostatics. So let's solve another problem that exercises the clear advantage of Ampere's law over Biot-Savart law. So as seen in the figure on the left, we have a cylindrical conductor with radius r that carries a current I towards the left. For simplicity's sake, this current is uniformly distributed over the circular cross-section of the conductor. Now we are tasked to find the magnetic field inside the conductor, where small r is less than big R being the radius of the conductor, and outside, where r, the field, well, the distance, is greater than big R, so clearly it's going to be a larger Amperian loop. We can split the problem into two cases. The first case where the field point is inside the cable, and B, where the field point is outside the cable. For the first case, note that our choice of Amperian loop and flow, the smaller one, makes sure that B is constant and parallel to DL throughout the contour. So for the next few problems, anytime we're going to solve Ampere's law problems, we're just going to assume that we pick the Amperian loop and the flow to provide us with the simplest solution as possible. This allows the sneaky pullout of B outside the integral, leaving the left-hand side to be equal to just B times 2 pi r, something that we've seen in the previous problem. Now, for the right-hand side, the loop only encloses the cylinder partially. So what does that mean for us? It means that I enclosed is actually smaller than I. It's qualitative, but then we're not really sure by how much is it smaller, by what factor. Luckily, the current I is distributed uniformly or distributed evenly across the circular cross-section, which means that the current density is constant. We can say that J is the same as J enclosed. Now, we take advantage of this by noting that J is equal to I over A by the definition of a current density, and since it's constant, is also equal to I enclosed over A enclosed. And all you need to do is isolate I enclosed. And by doing that, we have the following expression. We have I enclosed is equal to J times A enclosed, A being the cross-sectional area of the enclosed surface. And then, okay, we have an expression for J, it's I over A. I know that I is given, and A is just the circular cross-section area of the actual cylinder. So we have we have an equation that's rather simplifiable. The nice thing about this equation is I can cancel out the pi's, and then I can already combine the left-hand side and the right-hand side. So, well, before I do that, I'll express the complete right-hand side of uh, Ampere's law as mu naught times I enclosed is equal to mu naught times I times small r squared divided by big R squared. Combining the left-hand side and the right-hand side of Ampere's law, we have the following. B times 2 pi r is equal to mu naught times I times r squared, small r squared, divided by big R squared. And if we isolate B, it gives us B is equal to mu naught times I divided by 2 pi times r divided by big R squared. And note that this is the expression for the magnetic field inside the cable. For the second case, we employ the same process but then with a different Amperian loop. It's the much larger one, as you can see on the left. It's the circle with the radius small r greater than big R. Now, we end up with the same left-hand side, right-hand side pair from the previous case. And it's just equal to B times 2 pi r is equal to mu naught times I enclosed. Okay. So isolating B from the previous equation gives us B is equal to mu naught times I enclosed divided by 2 pi r. We still have to specify I enclosed. But then that's easy already, because I enclosed becomes trivial, or specifying it becomes trivial, since the bigger loop encompasses the complete current already. That means that I enclosed is equal to I. This leaves the case B, magnetic field to be B equals mu naught I divided by 2 pi r. And note that you have already seen this as the case for the magnetic field of a long wire segment. because when R is large enough, when you're far enough from the cylinder, that cylinder tends to look like a wire. Now, as a solving tip for future problems, the process of solving the magnetic field in configurations with cylindrical symmetry is largely similar. So what we did here can actually be applied to problems wherein you deal with cylinders. The thing is, solving coaxial cable problems, as seen in the lecture slide. So if you want an example of how a coaxial cable would look like, so its cross section is kind of like a combination of a donut and, well, a solid cylinder. So this is shaded. So this problem is seen in lecture 26. I invite you to try to solve it on your own. Now, solving these types of problems may require a different formula for the cross section. For our cross section in this problem, we dealt with a simple circle. Now, maybe for that the coaxial cable, you have to be creative in trying to determine what the area of the cross section is. And even then, it can be possible that parts of that cross section will have different values for current density. So you really have to be careful. So I invite you to try to solve them as a review for your summative problem sets. We're nearing the home stretch for the recap. For currents running through straight wire segments, notice that it's the magnetic field that circles the current. Say that we want the magnetic field to be the straight vector, or to be the one traveling constantly. So we try to simulate a bar magnet, for example. We go about doing it by turning the tables and letting the current actually coil around the magnetic field lines. This is usually done with a solenoid. A solenoid is basically a helical winding of wire with a circular cross-section. You may see some examples of solenoids on the left, or that's one example, a simple one. The top picture is a typical construction of a solenoid. The circling of the current is ensured by the helical winding of the wire. Now, the middle diagram shows the magnetic field lines of a loosely wound solenoid. So notice that the magnetic field lines inside or through the tunnel aren't really as straight, they're wobbly. And another detail would be that the magnetic field lines outside are actually leaking. So for an ideal solenoid, you'd want to make sure that the magnetic field lines are isolated through its tunnel. The bottom diagram has the wires tightly packed, as seen in the in-out vectors of the currents. So notice that the currents here are tightly packed, moving out and here moving in. This effectively straightens out the magnetic field inside the coil, perfectly simulating a constant magnetic field, and shutting out any leaks of magnetic fields outside of the solenoid. So for a detailed derivation of the magnetic field due to a solenoid of n turns per unit length, I invite you to review lecture 26. I'm just showing the end result. So it's B is equal to mu naught times n times I. So you have a reference for this recap. As with pretty much all of the calculations we've had so far, the direction of the magnetic field is determined by, you guessed it right, the right-hand rule. You curl your fingers in the direction of the current instead of the magnetic field, and your thumb will point in the direction of B. So if you look at the bottom diagram, I point my thumb to the right, and notice that my fingers will curl out of the page if it's above the magnetic field lines, and inside the page if it's below the magnetic field lines. So thank you for your time and following along the recap. I hope that this should be enough to get you back on track for the following lessons. One of them would be Faraday's Law, chapter 27. Lecture 27. Good luck and stay safe.